Howdy PreCal, it is Ms. Kosh, and today we're going to look at applications of exponential and logarithmic functions. And so we've kind of listed a few of the things that we typically see, the real world situations that show up and that make us work with exponents and logs. And the first one is when we when we compound money or when we're investing money, but it's compounded at anything that's not continuous. Okay, so on this one, this could be compounded daily, monthly, yearly, weekly, anything like that. On this one, this is where it's compounded continuously. Basically, what happens is the number of times that we compound it, instead of compounding it once a year or 10 times a year or 100 times a year, we've taken that number, we've gone from, from 1 to 10 to 100 to 1,000 to, and we just let that number go to infinity. And then it gives us this other equation where it's compounded continuously. If you want a better understanding of how this one becomes that one, I probably have another video. I might I'll go look and see if I do. If not, it's a little bit beyond the scope of what I only want to do with you right now. Then we also look at exponential growth or decay, and where we're adding we may say the population grows at a certain percent. So this might be population, or the number of bacteria or something like that. It's typically, the population growth, it could be money. These two are typically money. And this one is typically population or, the number of bacteria, the number of, I guess that's population. You could make this like the price of a car is increasing or decreasing. As you drive it off the lot, it decreases by 10% every year or something like that, and that would fall into this category. The other one is a half-life or double life formula. So you can have something, we often see radioactive things where the amount of radioactive substance decays by a half at this particular half-life. Okay, so a lot of these formulas use some of the same variables, so I wrote them kind of all down at the bottom. So A is our amount. You might think, maybe we should have said it's our final amount. Okay, so A is the final amount. P is our principal when we're talking money, or it's or A naught is our initial amount. And they kind of begin the same way, that they're both the initial amount. How much did we start with in this scenario? R is our rate. Okay, it could be the rate of the interest rate from these two with money. It could be our growth or decay factor. It could be the rate of growth or decay, the rate of increase or decrease, but that's going to be rate. B becomes our growth or decay factor. Okay, and so we use the rate right here to determine what our growth or decay factor is. So we would either, if it's a rate of increase, then we would add R. If it's a rate of decrease, we would subtract R. So we would start at 100%. If you're adding 10%, you have an increase. So you're at 110%, which becomes 1.1, so forth. Okay, N is the number of times compounded. Okay, so this could be I compounded it monthly, so then N would be 12. Or I compounded it semi-annually, N would be 4. I compounded it daily, N would be 365. T is time. And what the units are could change in the problem, but you have to be consistent within your problem. H or D is the half-life, the half or double life of whatever that thing is. And so if you've got this asymptote, or excuse me, not an asymptote, I was trying to say radioactive isotope. Oh my goodness. Okay, if you have something that's radioactive and it decays maybe every 1,000 years you have half of what you started with. That means your half-life period would be 1,000 years. Or you have some things that have a much faster half-life, and so maybe it has a half-life of 3 hours, and so that will tell you how quickly it's decaying, or how quickly we're getting half of it, or if it's doubling. Okay, so let's look at a couple examples, and we have our formulas that we can recall. An account with an initial deposit of $5,000 pays 3% annual interest compounded monthly. Okay, as soon as I see compounded monthly, that's putting me in this column right here. compounded, where it's compounded. Okay, so I'm going to use this formula. I'm not even going to write anything. I'm not even going to read the rest of the problem until I write down my formula. Okay, can we see this blue? Should I use a different color? You can't answer me, can you? You know what? I'm gonna switch to something darker just in case. So hopefully you could see what I was doing before. But it bleeds through, so I got rid of the rest of the papers. Okay, you didn't need to know that. All right, so here's what we know that we need to use this formula. And so it pays 3% annual interest compounded monthly. So compounded monthly tells us that n will equal 12. 3% annual interest means r equals 0.03. And this 5,000 right here, that means that our principal is $5,000. That's 5K, 5,000. Okay, so now we're gonna plug everything in. The amount that we have would be 5,000 times 1 plus r is 0.03 divided by 12 raised to the 12t, where time is in years. Okay, so now how much money will we have after each indicated time in the chart? Okay, so 1 year, this would be when t is equal to 1. 18 months, that's 1 year and 6 more months. So that is t would equal 1.5. 2 years, t equals 2. 30 months, okay. I see 2 years is 24, and so then that's 6 more than that. So this is where t equals 2.5 years. Here we have t equals 5 years, 90 months. Oh, hang on. 90, it's too early in the morning, I'm so sorry. 90 divided by 12 is, okay, 7.5. So that is 7.5 years. And then we have t equals 50 years right here. Okay, since we are about to have to do a whole bunch of equations, what I would do is I would use my table. And I could do this, and in Desmos, we could call this function, we're probably going to have to use f, or we're probably going to have to use x instead of t. And so I might call this f of x or a of x or whatever I want to call it, but then I can just do, remember how we've done it in Desmos? I could, if I called this f of x is equal to, and I wrote all this out and changed this to an x, I would probably then say, okay, then evaluate f of 1 and then evaluate f of 1.5. And I could type those in a little more quickly. I chose to do this where you can see my hands, and that means we're going to use the calculator. So what I will do is I will come to the table and type in this equation, 5,000 times, I don't know if I need that, but anyway, 1 plus 0.03 divided by 12. I prefer this, 1.03 divided by 12, and then I'm raising this to the 12x power. Okay, so here is my function. I can set the table and tell it where I want it to start and stop, which is fine, but I'm gonna have to kind of override some of these. So I'll probably just ignore that and go to the table. And so after 1 year, here's the first one. How much money do I have? I have $51.52, so $5,152. Nice. Okay, and then I need 1.5, so I can override that. And let's round it to the nearest penny. So I see 5229.85. Oh, this is going to start not fitting in my boxes. Okay, and then after 2 years, that's this. So that becomes 5308.79. 2.5, I'll have to override something. 2.5. I see. Can you see what I'm doing? I want you to see both the calculator and what I'm writing. Let me write it up here. So 5388.92. I now have to do, oh, you know what? Here's 5. Well, fantastic. 5808.08. That's a lot of 8s. Okay, now I need 7.5. I have to override that. So it's amazing how much easier this table is, makes it for us, right? Rather than plugging it into the equation each time. And then 50. Okay, ooh, I've got some money now. So, I mean, I've had to wait a long time. 22366.54. So 22. I've started at $5,000 and now I have $22,000. So your takeaway is invest early and often. Okay. After how many years will the account accrue at least $10,000? Okay. So what I would do with this one is I would come. The nice thing on, well, if you're in Desmos, you could then just graph the other line. Here, menu, I can come over to graph, and the equation that I wrote in the table world is still here. And now I want to know, when does this equal 10,000? So I'm going to have to change my window. So shift window. I need to have a y value. I need to be able to see that 10,000. So I'm going to plug in 11,000. And my x values are going to need to be a bit bigger. So I do know that in 50 years I got bigger than that, so I don't need to go as high as 50. We'll just go 40 and see if that works for us. Okay, so I'm graphing. Here's that curve. Oh, look. Okay, my goal was to be able to see where those two graphs crossed, and G-solve intersect. And here we go. What does that say? Sometimes I can't read all this, and so what I have to do, you can go menu and come back here, and if I tell it X and then enter, it will show me that number, and now I can read it a little better right there. Okay, so after how many years? 23.1338 years. So roughly 23, 20, I would probably accept, I mean, if you round down, at the beginning of 23 years, you don't have $10,000. At the end of 23 years, at the beginning of year 24, you do. So if it says round to the nearest whole year, then I would have to say 24 years. Okay, but I'll try and be clear as to what I'm asking you to do. Okay, let's look at the next one. You have $5,000 to invest in a bank account that earns 1.75% annual interest compounded continuously. Okay, as soon as you see, sorry, could you see what I was doing? As soon as you see the word continuously, you come back, and we are now in this second column right here, where this is compounded continuously. So before I even keep reading, this is the PERT. A equals P times E to the RT. Okay, so our principal, so A is going to equal, our principal is that 5,000. E to the 0.0175 T, and there's our equation. Okay, notice I had to change this, had to move this 1, 2 places. So 1, 2, there we go. How much money will accrue in 10 years? When will the account? Okay, so since I have 2 questions to do, like if I just had this one, I'd just plug in 10 and move on with my life. But since I have 2 questions that I need to answer, then I'm going to probably use my table or, I'll do it straight in graph. Okay, so we don't need these anymore. Oh, when did it accrue? 7,000. Okay, well, I can change this to delete, 7,000. Let's come back and type in our equation. We had 5,000. E is shift right here. So notice it was the natural log button. Oh, you can't see what I'm doing. I'm so sorry. Okay. E to the 0.0175, not 2 5s, X. Okay, so I can look at the graph. And so when I draw those, oh, look, the window that I created a second ago still worked for us. When will the account accrue $7,000? That would be that point of intersection. So when T is approximately, I see 19.226, 70, if we're rounding to 4 decimal places, years. So by 20 years, if you have to do to a nearest whole year, how much money will the account accrue in 10 years? What we can do here is we can do G-solve and go over to YCal. And I can plug in a 10. And so this tells me that I would have $5,956.23. Cool? Okay, let's keep going. I have more. Don't worry, there's more. Okay, so now we have, you are deciding between 2 different accounts to deposit $10,000. Lucky you have $10,000 to deposit. American International pays 1.65 annual interest that is compounded continuously. Okay, so compounded continuously, we look back at our table very carefully. And so compounded continuously is the A PERT. Okay, so this is A equals P times E to the RT. So we have our initial amount was $10,000, E to the 0.0165 T. Okay, and then Co-America pays, that's compounded quarterly. Okay, soon as it's compounded not continuously, we look at this equation. Okay, so this is, we're going to start with A equals P times 1 plus R over N to the NT. And this one, compounded quarterly, means that our N is equal to 4. Because quarterly happened 4 times a year. So we have our $10,000 still times 1 plus our rate is 0.0165 over 4 raised to the 4t. Okay, so what I might do, well, it doesn't really matter a whole lot. I can just type in these equations. You know, I'll do it that way. I could go to my table or whatever, but since they really are just, we're about to move on to a new problem. There's not, by the time I type it into my table, I could have just typed it in somewhere else. I didn't need to do it anywhere else. So let me just show you what it would look like in this regular world. Okay, so I have this 10,000, is that 10,000? Times e to the 0.0165 times 10, because we're plugging in 10. And here is, this is the American International. You can't see that it says that, but that matches this box. And so now I have $11,793.93. Okay, the other one, I'm going to plug in 10 for a t there. So I have 10,000, I think that's 10,000, times, well, let's see if I don't have to put the times. 1 plus 0.0165 over 4 raised to the 4 times 10 is 40. Okay, and so now after 5 years, I have 11789.93. Also, how close were they? I mean, this one's better, but not by much. So what we would find is, okay, now I wish I had typed them in over here. We're going to delete this. We're going to delete this. We have that 10,000. I just want to show you that they would cross somewhere. Shift natural log e to the 0.0165 x. Right, that was that first equation. And then the other one is 10,000 times 1 plus 0.0165 over 4. I think if I don't type this incorrectly, oh, wrong, like that. Let me know. Raised to the 4x. When I graph these, okay, I need a different window. I need, let's call it 20,000 as a max. And I bet our x value is okay. That is more similar than I expected. Well, I guess starting with $10,000, they're not the same. Hang on, let's see. Let's change our window again. Let's go from 10,000 to 20,000. See if that, for our y values, let us zoom in a little bit more. No, they still look the same. They're not. Okay, let me move on. I'm sorry. I'll think about that and see what I can do for you. Okay, the next one, a scientist has 20 grams of element X. The half-life of element X is 40 days. Okay, so as soon as I see half-life in my problem, I'm now in this column. And the half-life in particular is this A naught times 1/2 to the T over H. So A is equal to A naught times 1/2 to the T over H. I usually don't like fractions written this way, but sometimes when they're exponents, it's hard to, like, it just gets too cluttered. So I kind of go like that. Okay, so we have, a scientist has 20 grams. The half-life is that. Write an equation to model this. How many grams remain after 100 days? Okay, so we have our initial amount of 20 grams. I wasn't sure. I had to keep reading, to be honest with you, to know if they meant this was the initial amount, or they're like, we have 20 grams left now. We want to know how much we started with, but they didn't say that. So how many grams remain after 100 days? Okay, so we have 1/2 times the time. We don't know how long the time is, and our half-life is 40 days. So there's our equation. So basically, we want to find A when we have, this would be after 100 divided by 40. That's the formula that we want. How long would it take? So you know what? Since there are two questions, we could either plug this right into our calculator and figure it out, or we could come back to clear this mess out. Oop, exit. Type this in, 200 times 0.5 raised to the, I was too lazy to type 1/2, I'm sorry. Raised to the x over 40. Okay, so here's my equation. I can draw this, let's see, okay, let's change our window, shift window. I need 100 days, so my x's are, let's do it at 120. And let's go from, we're not gonna have more than, let's go from -20 to, we had 200 grams to begin with, so let's go to 250. So we're a little bit bigger than that. Okay, there we go. There's our exponential decay problem, or our graph. I want to know how much remains after 100 days. So G solve, we're going to do a Y cal. We're going to plug in 100, not 10. And when I do, I get this. I find that the amount is about 35.3553. What are my units? Grams. Cool. Okay, how long would it take for only 15 grams of the element to remain? What I can do is I can come back here and say, when will the amount be 15? I can draw. Oh, okay, I need to go farther out with my window. Let's go to, I don't know, 200. Okay, there, now I see them crossing. So G solve, intersect. And they intersected, how long? Time would be about 149.4786 days. So 150 days if we ask you to round to the nearest whole day. Cool, I have one more example. What do you think it would be? Well, we haven't done one from the double, or, oh no, we need to do one, let's see. The culture initially, okay, so on this one, oh, it doubles every 5 hours. Okay, so doubles every 5 hours is going to be this one. And that was A is equal to A naught times 2 to the T over D. Because that's here. Could you see it? Okay. Move that clutter. How many bacteria would there be after 1 day? So, oh, I forgot to fill out the numbers. So A will be equal to the culture initially, that's our initial amount, 3 times 2 to the, it doubles every 5 hours. So this is going to be T over 5. How many bacteria will there be after 1 day? Well, 1 day is 24 hours. And so we need to make sure that our time is consistent throughout this. If I used 1 to put in here, I would mean 1 hour out of the 5, so it'd have a fifth of the time. Okay, how long would it be for there to be? Okay, so let's do the same thing. I think I can delete this stuff. What was it? 3 times 2 raised to the x over 5. I can type it in that way. Oh, and it fixed it. And then eventually I want to know when will there be that many bacteria? Is our window going to be good? No, it's probably going to be wrong. Let's think about this. Let's change our window. So shift window. I mean, maybe we need to go to 200. But my y value, they're asking me to go to 1500. So I'm going to go to 2000 for a y value. Okay, I had too many x's, but I can do what I need to do. So the first thing, to answer the first question, I'm going to do G solve y cal. Yes, that's the equation I want, 24. And so I see at 24 hours, I'm going to have 83.5729 bacteria, but that doesn't make sense. Bacteria don't come in parts, I think. We would have a whole bacteria or not. So I could see an argument for 83 or 84 bacteria. I would probably accept either answer, but let me talk to Miss Bellish and see what she's going to do so that we can be on the same page. Okay, how long would it take for there to be to 1500? So G solve intersect. So I think I see 44.8289. So about 45 hours. So not too long. Bacteria is going to take over. All right, like, subscribe, comment, and let me know how I can help you. And of course, the only way to learn math is to practice. Go practice.